Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, Dave Ansell and Chris Smith. Now, Dr. Chris, Dr. Dave, first of all, Tony from Walpole would like to know what a heart murmur is.
OK, this is a sound that you hear when you listen to the heart, Sue. When doctors examine someone's heart, they do so usually with a stethoscope. And the stethoscope, all it is, it looks fancy, but it's just a tube that connects your ears to the person's chest. And it was invented a few hundred years ago by a Frenchman, Laennec, actually, because it was socially unacceptable for a doctor to put his ear too close to a woman's bosom. And so he started rolling up notes of papers and putting those as a tube between the skin and his ear, and discovered that that worked quite well, but it looked more elegant if you had a nice wooden tube to do it. And in more recent years, because a wooden tube stuffed into your pocket's more difficult to carry around, looks impressive, makes an impressive bulge in your trousers, but is not necessarily very practical, then the stethoscope was actually adopted. What it consists of is on the end of the stethoscope there's a flat membrane. This is applied to the surface of the body, and when something moves or there's some sound vibrations coming from something within the body, it's transmitted to the skin surface, and it then transmits onto that membrane and makes the membrane vibrate. And the vibrations in the membrane, a bit like the eardrum in your ear, carry that sound up the air inside the stethoscope to your ears. So it's just a useful way of screening out room noise and just letting you focus on the noise coming from the patient. Now, if you use a stethoscope on the heart, you can hear the heart working. And when the heart beats, if you put your hand on your own left breast, just underneath the breast if you're a woman, you'll feel there's a sort of double pulsation. There's a thump and then a bigger thump. And what's actually happening is that, first of all, the heart has two chambers at the top called the atria, and these are where blood flows back in from various places. In the right side of the heart, it flows in from the rest of your body. In the left side of the heart, from the lungs. Those atria fill with blood, and then they squirt the blood into the two main chambers in the heart, which are the ventricles. And the ventricles then contract and squirt the blood either on the right side of the heart round your lungs or on the left side of the heart round your body. So you hear several sounds, and that's the sounds of the blood or the valves in the heart moving as the blood moves around the heart. So you get a lub-dup sound. Now, when you have a heart murmur, what can happen is that you can hear the blood actually moving through the heart more loudly than normal, or you hear the blood moving through a valve more loudly than normal. And there are several different types of murmur. Some of them are completely benign. They don't mean there's anything wrong at all. They're just because the heart's working fast. Others are more pathological, and they can signal things like a leak between the two chambers of the heart or a leaky valve, and it's just turbulence. So when fluid flows through from one part of the heart to the other, it gets turbulent, and those turbulences create vibrations that the doctor can hear, and it just sounds like a sort of rushing or a whooshing sound, a sort of noise. And it's depending upon where you hear it in the heart cycle, it tells you which bit of the heart is playing up, and therefore where the problem is.
I used to go out with a girl who had a hole between, I'm not sure which parts of her heart, but that really sounded like quite a high-pitched squeak. Was that because the hole's quite small?
That's correct. You quite commonly find people who have what's called a hole in the heart, and because there are two sides to the heart, there's the right side and the left side. The left side of the heart pumps blood around the body, and the right side of the heart pumps blood around the lungs. Normally what happens is that it goes out of the right side of your heart, through your lungs, into the left side of the heart, and then out round the body. But in some people, there's a small communication which can occur between the main ventricles, the right and left side. And because the left side of the heart runs at a much higher pressure, because it's got to push blood right the way around the body, than the right side of the heart, which just has to push blood around the lungs, because there's that pressure difference, sometimes you can end up with blood being squirted through this tiny hole between the two ventricles from the left side to the right. And again, it causes turbulence because the flow isn't normal, and it makes this sort of whooshing noise. And depending upon the size of the abnormality, you get a different sound. And paradoxically, a very big abnormality makes much less noise than a very small one.
Right, OK, that's put us there. Thank you very much indeed, Dr. Chris. We've had the Beaver Scouts come round today as well, and they have poised a question for Dr. Chris and Dr. Dave here on the Science Uncovered. They would like to know, how many stars are there all together
The current NASA estimate, which goes back about 4 or 5 years, is over a heptillion stars. So they think about 7 heptillion. That's 7 followed by 22 zeros. So a rather large number. That's just stars in the known universe. In our galaxy, the Milky Way galaxy, we think there's something like 100 to 200 billion. So even in our cosmic neighbourhood, there's a huge number of stars in this neck of the woods.
That's quite amazing. Have you got anything to add to that, Dave?
And I guess of those, how many heptillion? 100 heptillion?
Seven heptillion, so 7 with 22 noughts after it.
Yeah, of that, you can probably only, if you've got really, really good eyes, like those beavers, probably you could see maybe 10,000 of them, 10,000 of them. If you're up a mountain, and sort of, with our eyes, probably nearer 4,000 or 5,000 at the best.
But how they do see them is with amazing space telescopes like the Hubble. You can look deep into space, and because they haven't got the problems of light pollution and the atmosphere getting in the way, they can do these very long exposures looking deep into space, and you see these amazing pinpricks of light. And just by counting how many dots there are in a small part of the sky, you can then extrapolate to how many there must be in the whole of the sky, and it's going to be a conservative estimate anyway. But what I find really exciting is that a reasonable proportion of those stars will be very similar to our own sun. And if there's stars similar to our own sun, and that means they have very similar lifetime, in other words, they're long-lived stars, that means that there's the opportunity to have planets around them, and that means there's the opportunity for those planets to have life, because what you need is a stable cosmic setup. A bit like the solar setup we've got here in our cosmic neck of the woods around our sun. It's a sun which is going to live for about 10 billion years. It's just the right size, and we've ended up with a combination of planets that's in a stable configuration with the Earth just the right distance from the sun, so it gets the right amount of heat so that we can have liquid water on Earth, and we also have a nice big moon to keep our planet spinning stably. So we're very lucky, but with that many rolls of the dice, I find it almost impossible to believe that there's not other Earth-like planets out there around stars a bit like our sun, which means there's almost inevitably got to be something a bit like life drifting around out there in space somewhere.
Ooh, Dr. Chris, that might be opening a can of cosmic worms there. I find that's great.
I rather hope not.
No, but I think that's great that you've made that revelation here tonight.
When I was in St. Louis, actually, Sue, and this is in St. Louis in America, when I was there for the AAAS, that's the American Association for the Advancement of Science meeting, about 2 years ago. It's about to happen next week, actually, in Boston, and we're going to be there. I asked 3 scientists who were presenting in St. Louis their work, and they work on the very subject of looking for life outside of our own solar system, what they thought the chances were of us discovering either a hallmark or direct signs of life outside our own solar system within our lifetimes. And their answers ranged between 5% and 15 to 20%. So that's actually very big numbers, given that we're talking about our lifetime. So we're talking in the next 40 or 50 years, and we're also talking about a reasonably high chance of that happening. I mean, 15%, 20%, that's a 1 in 5 chance. That's very high odds. And these are people who are working on this.
But of course, finding intelligent life that's at least as intelligent as us is probably going to be much less likely. Because just looking at the history of life on Earth, there's been life on Earth for sort of 3 billion years at the very least. And as far as we know, the only time when any species as intelligent as us, or at least as able to manipulate the environment as us, after 3 billion years, it's only been the last 10,000 years that it's happened. So it's probably very much more rare than life itself.
That's true, Dave, but then you think about it, the actual universe itself is about 14 billion years old, and, in other words, that it's 3 times older at least than our cosmic setup is. So I think the odds are pretty good.
I'm not saying there isn't, it's just we're much more likely to find life than intelligent life, I think.
Mike has sent a text in, and he says, Dr. Dave, I looked to the sky last week, western side, and I saw one of the stars was blue, and also, what star in the east looks red?
I think I think Mars is probably rising in the east at the moment from my quick calculations. I might be wrong. Mars definitely looks noticeably red, and it's quite close to us at the moment. So probably the red star in the east was Mars. I'm not so sure about the blue star over in the west. The various stars can have a slight bluish tinge. They're very big stars which are running very, very hot. You might have noticed that if you get something slightly quite hot, it goes red. A bit hotter, it goes orange. If it gets really, really hot, it goes white. If it gets even hotter than that, it starts to take on a bluish tinge. So the really, really big, very, very hot star, or the very, very fast-running, very, very hot stars, tend to have a bluish tinge. I'm not sure which one it would be, because I'm afraid my knowledge of the night sky isn't that good. But I don't know if Chris got any clues.
No, I like your idea about Mars, because of that is, of course, very much the red planet, and that does sound like you're on par with that. The blue one, not sure what that would be, but we could actually have a look, because there are various websites now where if we had the coordinates, we can put it in. So if we can get the coordinates for where those stars were seen, we'll try and find out.
Right, Mike, so if you've got the coordinates, or to a brief. So when you say coordinates, you want the, where he was standing when he looked west?
Yeah, if we can work out vaguely where, what you can do is to plot these on various websites, and they will tell you what stars are where at what time, and you can therefore identify the night sky. So if you just type into a search engine, star finders and things, there are quite a few of these now, which will help you to track down what planets and what stars are what at what times, depending upon where you are on the Earth, because of course if you're in the southern hemisphere you see a different patch of sky than if you're up here.
Now then, why do your fingers go wrinkly when you stay in the bath too long?
This is a really good question, and it's all to do with the structure of your skin. Bits of the body which get a lot of wear and tear, so a lot of friction, tend to build up a thicker protective layer of skin than bits of the body that get less friction. So if you measure the thickness of skin on, say, the palps of your fingers or the bottoms of your feet, because they're rubbing on things quite often and they need to be able to handle more stress, the tissue there is thicker. Now, if you zoom in on the skin with a microscope, you'll see that it's very, very interesting structure, because it consists of flattened dead cells. In fact, you're shedding millions of these over the course of a day. Every single minute or so, you lose something in the order of 30 or 40,000 skin cells. They just drop off your body and turn into dust in the environment. But if you look at these cells, they're born deep down in the skin. They get squashed, flattened and dried out and dead, and then they form these layers, which is your skin. And that's why you can rub off layers of skin and it doesn't hurt too much until you get down to the very lowest levels, and then it starts to bleed. So there's a lot of dead skin on the surface, and that's what protects you and gives you something to wear away, if you like. And the skin cells are being replaced at exactly the same rate as they're being worn away. So the skin is in balance. But because those cells are dead, but they still contain material and proteins and things, when you go in the bath or in the water can get in through the surface layer of the skin, and it begins to soak into the cells. And in the same way as if you put something, say a sponge, in the wash, it can soak up water and swell a bit. The skin swells a tiny bit. And it's a bit like railway tracks, which buckle on a hot day. The railway tracks expand, and if there's not a big enough gap between the rails, then they can bump into each other and begin to warp. And the same thing happens with your skin. The skin gets pulled into all kinds of ridges and furrows as the skin tries to expand to accommodate the water that's moved into the superficial layers. So that's why it's principally the fingers and the feet that get affected, because there the skin is extra thick to accommodate the wearing away, because we use our skin on our fingers and feet all the time.
Right, that answers that one. Now then, another one here. What holds the universe together? Asked Ken of Hockley, and also a similar question from Clive of Wattisham. Both say that surely you can't travel forever without hitting a wall of some kind.
The force which tends to pull the universe together is gravity. It's the same force which tends to pull us towards any other kind of massive object, and the biggest massive object near us is the Earth, so we're getting pulled towards the Earth quite strongly. We're also getting pulled towards the Moon a bit, and a bit towards the Sun, and in fact towards everything else in the universe at once. So everything, for example, in the galaxy, everything is being pulled in towards by gravity, and it's probably going to keep on coming in. But actually, astronomers just seem to be finding in the last few years that the force of gravity doesn't seem to be holding the universe together. As far as we can tell, the universe is actually expanding, and it's not slowing down as gravity gravity pulls against it and slows it down. It actually seems to be accelerating. So billions and billions of years ago, the universe was expanding slower than it is now. So over time, the universe seems to be expanding faster and faster and faster. And as far as we know, the universe will just keep on expanding faster than gravity. Faster than gravity can't hold it together, so it's just going to keep getting bigger and bigger and bigger until after a while we won't be able to see anything other than our own galaxy after billions and billions of years. And there was also a question about whether we can keep on going without hitting a wall of some kind. As far as we can see, there's no wall. We can keep looking back until we can see. We keep looking 13, 14 billion light years away, and you can't see any wall. Beyond that, we've got so far back in time that you start seeing the remnants of the Big Bang, which were opaque, so we can't see any further. But as far as we know, there's no edge to the universe. That could mean a couple of things. Either it could mean the universe just goes on forever. It could also mean that the universe, our 3 dimensions in our universe are sort of like the surface of a sphere in more dimensions. So if you so in the same way as on the Earth, if you keep on walking in one direction, you'll get back to where you started. It could be possible that the universe behaves a bit like that, and if you go off in any direction for far enough, you'll end up roughly back where you started. But but astronomers don't seem to haven't been able to decide whether the universe is infinite or whether it or whether you keep on going one direction, you come back to where you started again. But we're not absolutely sure whether there is any kind of wall, but as far as we know, there isn't.
Right, okay. We have Alan on the line. Good evening, Alan.
Hello, Sue.
Hello there, you're through to Dr. Chris and Dr. Dave. What's your question?
Just recently we're hearing that in the near future we're likely to get this 2-ton spy satellite coming through the atmosphere and crashing into Earth somewhere. It then sort of generates the thought, well, there's lots and lots of debris out there that we've been sending up that is either redundant or out of control. I want to know, is it all moving in the same direction at the same speed, or can it collide with each other? Or do we know where every bit is and how much of it there is? And how much of it comes back to Earth along with this 2-tonner that's on its way?
It isn't all moving in the same direction, and definitely not at the same speed, because for an object to orbit the Earth, basically an orbit, things normally fall towards the Earth, but if you can make it go so fast that by the time it's fallen down, it's actually missed the Earth entirely, and it's out over the other side, and so now it's falling in a different direction, and it keeps falling towards the Earth, but it never actually drops below a circle. That's an orbit. There are various different orbits. So the traditional one which you think about is just going around the equator. I think mostly those will be going in the same direction, so they're going roughly at the same speed. But there are also other satellites which you can't see the poles if you're going around if you're orbiting the equator, because you're never above them. So there are other satellites which orbit around the poles, and so they're sort of going in a circle on a completely different axis. So they're going at a completely different speed in a different direction, and also at different altitudes. If you're orbiting at a low altitude, you've got to go a lot faster because gravity is stronger, so you've got less time to miss the Earth, so you've got to be going faster than if you're at a much higher altitude. So if you're just at a couple of 100 kilometres above the Earth, you've got to orbit the Earth every 90 minutes or so. But if you're up at about 36,000 kilometres, you've only got to orbit the Earth once a day. You've got to go further, but you're still moving more slowly. And so, yes, there is a lot of junk up there. It's not much of a threat to us unless it comes down in very, very large lumps, and even then you've got to be very, very, very unlucky for it to actually hit you. It's a much bigger threat to other satellites because the speeds are so large, because the orbital speeds are sort of 13,000 miles an hour or so. You only need a tiny, tiny particle to actually do serious damage. The windows on the shuttle are sort of 2 inches of armour glass. And a little paint fleck hit one sort of 10 or 15 years ago, and this little paint fleck was going fast enough to shatter several layers of this armoured glass and really craze the surface. I mean, just something weighing 1/10 of a gram going that fast can do an awful lot of damage. They are tracking all the objects bigger than sort of about 10 centimetres, I think, with radar. And if, for example, the space station, if they calculate the orbits of these little bits, and if they see an orbit which is going to come too close to the space station, they'll actually move it so as to make sure it doesn't hit it.
Have they got that level of control then?
They can definitely move it by a couple of kilometres. If they've got enough warning, so a couple of weeks, they can move it several kilometres out of the way, and so it will definitely miss it.
Now, they say what goes up must come down. Is it possible that some escapes out into space and never comes down?
I think it's quite unlikely that... I mean, in our lifetimes, a lot of it which will never come down. The stuff up at geostationary orbit, I think it'll take sort of 20 or 30,000 years to come back and to generate its orbit to degrade enough to hit the Earth.
But there's going to be a massive amount of stuff there by that time. I mean, it'll be almost... They'll be sort of parked side by side virtually, won't they?
Yeah, I mean, there is a big worry that if we keep on sending stuff up the rate we are, especially if people like because the Chinese blew up a satellite recently, and that produced lots of small bits of debris moving fast and moving on random trajectories. And so there is a big worry that, not that it'll cause us any problems on Earth, but we won't be able to send up any more satellites because they'll just keep getting hammered by all these little tiny bits of other satellites crashing into them. And there is a big worry. There have been people talking about going up and basically trying to tidy up all the satellites the old dead satellites, and at the moment they tend to put them into a parking orbit. So, especially in the geostationary orbit, because it'll take so long for them to degrade, when the satellites are just before they run out of fuel, they'll fire the rockets and move them out of the way of the geostationary orbit. So they're doing a different orbit. It's not in the really expensive and useful orbit which stays over the Earth as it rotates. So they can go off and crash into each other in the parking orbit. But if we keep on sending up stuff at the rate we are now, we will get to the point where you're going to have to arm all your satellites before you send them up, because they're just going to get hammered by all these little bits of debris.
Interesting stuff. Alan, thank you very much indeed. Bye. Bye. Now then, Dr. Chris, very quickly, Tony from Westcliff asks if in his day, because he's 83, he said when every product carries a sell-by or eat-by dates as opposed to when he was young, if something was slightly off, they would just smother it with vinegar or pepper. Does all the present-day fussiness make our immune system weaker?
Well, I think if you pay a visit to a Victorian graveyard and take a look at the infant mortality rates and the number of people who didn't live very long 100 years ago, and you look at the average lifespan today, you'll realise actually the giant strides that have been made in controlling infectious diseases, because they were a major killer for mankind. And in fact, it's just better living which is making us live longer. Medicine hasn't had a huge amount to do with it. It's better living, cleaning up sewage and giving people clean water that's actually translated into longer living. And as well as that, when I say better living, I'm of course including better nutrition in the sense of food that's good and wholesome to eat. In fact, today we're in danger of doing ourselves a mischief, because the good work that's been done in the past is now being rapidly unravelled, and people are eating far worse in terms of the amount of salt and the amount of fat in their diets than they did before. And also people are taking less exercise than we did historically. So the consequence now is that we may have lived as long as we're going to live, and now we're going to start living shorter lives as we go into the latter part of this century. So there's an encouraging thought, isn't it? But
absolutely.
In terms of sell-by dates and things, the reason we have these is because once upon a time, when you shopped at your local shop, you could be pretty sure that you knew when a piece of meat had come in, it would sit in the shop, the shopkeeper would be the person who sold it to you, and the number of hands it had gone through would be very, very low. And people were pretty fussy about what they would and wouldn't buy. At the same time, nowadays, you have mass transport, you have mass production, and you have mass marketing. And this means that some of the food reaching our shelves could already be months old by the time we eat it. In some cases, vegetables really are. And you have cases of, for instance, prawns and other things being caught off the coast of Scotland. They're then shipped to Thailand, where they're prepared, and they're then shipped back from Thailand to the UK for sale. And that's scampi for you. I mean, this is ridiculous, but by the time you eat that, it's months since it left the seafloor. So when you have those kind of situations going on with food being passed from hand to hand through multiple suppliers, you need some kind of control, because if people aren't careful, if food isn't looked after, and when you're not the person who's got to eat it, it's easy to think, oh, well, what the hell? Then it's very easy for infection to creep in. And things that contain a lot of protein, like meat, things that got a lot of fat in them, like meat, they're very good for bacteria to grow on. And the kinds of organisms that cause food poisoning are not the same organisms that cause food spoilage. So when you look at food and it smells a bit iffy, that's a very bad guide as to whether it will actually make you ill or not. Because the kinds of things that make you very ill often are at low level. They're not very easy to detect. They don't give themselves away. They don't make the meat look manky or look a funny colour. But they can be there and they can infect you. And so that's why we have these sell-by dates, and they are cautious, and they're purposefully cautious. And what I mean by that is that companies set them so that they know that you could, in the same way as an aeroplane puts enough fuel to go from one destination to another and then half the journey almost again, it's the same with food. You have a huge safety margin built into the sell-by date. So if you have a yoghurt and it's 2 days beyond the sell-by date, the chances are it's absolutely fine. But the company who put those sell-by dates on are doing that just to cover themselves, to make sure that people don't get ill. So on the one hand, they're doing a very good thing. On the other hand, they are actually maybe making us a bit overcautious. Whether these sell-by dates are contributing to your immune system being less good than it could be, I think there are lots of other aspects of our lifestyle that's probably contributing to that. Probably living a very cushy lifestyle in an air-conditioned and centrally heated home with antibiotics given like Smarties has probably had something to do with why we have so many allergies today.
I wish I didn't have the cold I have. Chris, that's fantastic. Adrian from Durham says he wants to know, how do the TV and radio bosses know how many people have listened to a particular programme?
Well, it's all a big con, actually, and I probably shouldn't be saying that as someone who's on the radio, but the answer is you do it by survey. So in the same way as you might go out and ask X number of people who they're going to vote for at the next election, and you know roughly how many people you've asked, you know how many people live in an area, and you can say, well, that makes up 5% of the total target area. Therefore, if we multiply that number by 20, that will tell us what 100% would be. And so it's similar with radio and telly listening. They will poll a target audience, and these people will be asked to record or to give information about what they watched or what they listened to at a certain time of the day and night. In some cases, they're issued with diaries, and a certain number of people are asked to fill in a diary detailing what radio programmes they listened to. This is called Radar. It's the company that do this. And this is compiled to make listening figures. Now, the thing is that when you're doing that kind of thing, it is potentially quite flawed. And if you look at the absolute numbers, they could well be misleading. But what isn't misleading is the trend, because the absolute errors are probably going to be very similar from one assessment period to the next. So if you compare one assessment period with the next, the errors will cancel each other out, which means the trend or the sort of pattern that emerges will be meaningful, but the absolute numbers could be quite meaningless. So really you can use this as directional information to tell you whether your programme is doing well or badly. If the numbers are going up, that's probably a good thing. If the numbers are going down, that's probably a very bad thing. If numbers are going up, they can of course go up because people are listening to hear how bad something is, so it's not always a good thing. But that's pretty much how they do it. And the reason people were so excited with the internet revolution and sort of digital downloads and on-demand listening, things like podcasts, this is good because when people download it, we can track exactly who's downloading what and where they are in the world, because when their computer dials our computer and says, can I have a copy of your program, our computer extracts all of the data about their computer from their computer. So we can see geographically where, who, when and how much people are downloading of what. And this means that advertisers, whatever, people marketing, people trying to follow up and evaluate how programs are performing, now have a much more powerful tool because they know who is watching what for how long and when, which means that they can work out whether their programs are any good or not much more effectively and much more accurately.
Excellent. Thank you for that, Chris. Now then, Ken says, how many litres or gallons are there in a barrel of crude oil, and how much diesel or petrol do we get from one?
Do you know the number of gallons in a barrel?
I thought it was about 10, but I might be right. Maybe it's a bit more than that, maybe 30 or 40. I think it's about 40.
Dave's doing a quick few calculations. Have you worked out the oil ratio of diesel?
A barrel's about 117 litres. It's 31 US gallons, about 24 of our gallons, I think, in my head. And if you're the yield, it'll depend on what kind of crude oil you're putting into your refinery, because the crude oils from the North Sea will give you more petrol from them compared to a crude oil from the Middle East. But about sort of 40-50% of crude oil will come out as petrol if you don't then do anything else to it. Sometimes you can get very heavy, sticky oils, which you then break up and turn into petrol as well. But sort of 40-50% is fairly normal for what you're getting out as petrol from a crude oil.
All right, so that's about 50 litres then?
Yeah, so sort of,
half and
50
half.
litres, yeah, about half and half.
All right, lovely. A compulsive disorder here from Gus. He says, the son of a family friend suffers from obsessive-compulsive disorder. What exactly is it and how is it caused? Is it a chemical imbalance in the brain which makes people neurotic in this way?
The OCD is what this is, obsessive-compulsive disorder.
Yeah.
It's not that well understood, except that we know clinically what it means for patients who are unfortunate enough to be affected by it. So obsessive-compulsive disorder is where someone has an obsession, and their obsession drives them to, or compels them to do something. So the obsession might be, if I don't do X, then something horrible is going to happen. And in order to make their obsession better, or to make themselves think that it's not going to happen, their compulsion will normally be some kind of behaviour that assuages that anxiety. So some people, for instance, have obsessive-compulsive disorder about germs. And I was at medical school with a guy who had to keep washing his hands because he was worried that things coming off of door handles and things he was touching were putting germs on his fingers, and he was worried that they might get into him.
Yeah.
So this was leading to compulsive hand washing. So he would have to ritualistically wash his hands and dry them at least 5 or 6 times after he'd been to the toilet or after he had been in the shower even, before he could go back into his room. And this was a problem for everybody because he would prop open all the fire doors between the bathroom and his bedroom so that he didn't have to touch any door handles. And this was, of course, a fire risk, because once the doors were all propped open, he would leave them like that. So this was a problem for everybody else because it was risky. Exactly why it happens, we don't know. There are some drugs and certain antidepressants which can be used to make things better. People can get rid of these intrusive thoughts, these obsessions which make them want to do these things. But they're very disabling for the person who has them. If you can imagine, some people have to get dressed and undressed 15 times before they go to work.
Yeah.
Otherwise, they fear that something horrible is going to happen to them or their family, or something terrible will result. And this takes enormous amounts of time. I've seen patients who will get up at 4 o'clock in the morning in order to go through all their rituals so that they can actually leave the house in the morning. And they get exhausted, and it's very frustrating for them, and it totally interferes with their life and their relationships. And so people are very eager to try and find out what causes this. It's not a trivial problem. But luckily, as I say, there are some drugs that will, in some cases, make it slightly better. And also certain types of counselling can help people to develop strategies that help them to stop these things getting so entrenched, or to get around, find alternative ways to deal with their problem.
And Keith from Kettering says, is there any truth in inland wind farms blocking military radars? If so, will it mean the end of wind farms or military radars?
A radar will get... if you put anything large and metal in front of a radar, it will act as a reflector, and you can't see what's behind it. So a big enough wind farm will tend to stop the radio waves. In fact, they use microwaves for radar. It will stop them in the same way as the metal box around your microwave keeps the microwaves inside your microwave oven, and so you don't get cooked by them. So if you put something big and metal, like a wind turbine, up near a military radar, it will tend to interfere with it, get in the way. The other problem you get is that military radars, especially the clever ones, are very good at picking up things that are moving, because if a signal, it sends out a radio wave at a certain frequency, essentially a pitch, and if it bounces off something which is moving, it will come back at a slightly different pitch. So the military radar picks up those differences, so it can tell you how fast an object is moving, and so it knows that if something's moving at you quite fast, then that's something interesting, and you ought to be worrying about it, especially if it's doing about 500 miles an hour, because that's probably a plane coming to get you. So because wind farms are moving, then it won't only get in the way, but also get lots of extra movement information, which can confuse these radars. They were definitely very worried about some offshore wind farm, which was near a air base, because that was going to limit what you could see when you're looking out to sea and planes coming to attack you. But so it is an issue. I think they'll probably improve the radars rather than stop the wind farms, though.
All right, and okay. Is it possible to fit an alternator to an electric-powered car to charge the battery as you're driving along to eliminate the need for charging and lengths?
This is an old chestnut, because this is all about conservation of energy, because the fact is that if you are driving your car, you are using energy. In other words, stored energy saved from a battery, and it's got to go through a motor, and that motor is going to turn the wheels of the car. Now, at all stages, there is going to be an inefficiency. There will be inefficiency in the battery, there will be inefficiency in the motor, and there will be inefficiency in the car, and it will lose energy to air resistance. So if you try and recapture that energy to turn it back into electricity again, to put back in the battery, then what you've done, if you make that work, is create a perpetual motion machine, which we know can't possibly exist. So, no, it's not possible.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.